Are you able to hear me well? Are you able to hear me? Yes. Okay. You have to get used to my accent. That's fine. Okay. Because the response was not immediate for my second question. Okay. First, it's a pleasure to thank Dr. Sumit and the principal and the college for the invitation. It has been wonderful to be with you. So, as when told, the title of my talk is What Makes Real Analysis Tick. But then, when I say real analysis, you should understand what is the meaning of the question. Because when I say why my heart takes, that's a different answer. But when I say why smartphone takes, that's a different answer. When I say why heart takes, I want to understand why it works, how it is. When I say why smartphone takes, I'm not worried about how it was, why it is very popular with all of us. You understand? So what is the meaning of my title? Is the first one or the second one? It's the first one. Okay? It's not the second one as our Principal Sahib would like to have. Okay? That will be a separate issue. Okay? Because you just want to take this. Is that understood? Because we should know what our expectations. Okay? If your expectations are different, you will be disillusioned, disappointed. Okay? So your expectation should be, the answer to the question will be, or the meaning of the question is the first one. Why it works, not why it helps. Is it understood? Okay. Right. So since all of us know, I will give you a one-word answer. Okay. I will introduce the word and we will discuss about it. From Sumit, I understand that you have all gone through some analysis. Can I assume? Don't worry about how much you know or how well you know it. That doesn't matter. Some kind of what Americans would call nodding acquaintance. The word doesn't sound unfamiliar. Yes, that's good enough for me. Okay? I mean, I'm nodding the Indian way, not American way. Okay? Right. So, the first thing is, all of you know something about natural numbers. Then we contributed the greatest thing, 0. Then we had integers. Then we had the so-called rational numbers, fractions.
So we are not able to hear you.
See, that's why I am good. Can you slightly increase? No, that will be difficult for me. Okay. Is it possible to raise the voice at the back? But make sure that doesn't. If I walk around, will you be able to hear me better? Yes. Okay, good. That's what I usually like to. Okay. So next came the so-called real number system, right? Just vaguely, if you think, they look very similar. What I can do, I can add, I can multiply. If it is non-zero, I can also reciprocate, right? I can find a so-called multiplicative inverse. Then it becomes a field. I'm sure all of you know that word also, right? And also I have the so-called order relation. Given any two rational numbers or into real number, there is an order. And then law of trichotomy holds. Give me two real numbers, two numbers, either rational or real. I know either they have to be equal or one is less than the other, and exactly one of them must happen, and only one of them will happen. Is that right? So it looks so similar. Then why you don't talk about rational analysis, you talk about real analysis? So there is something special, right? That's the property you want to talk about. Okay? That property is, all of you know, is called the least upper bound property, and sometimes the textbook may call it order completeness. Okay, slightly reduce. Is there an electronic disturbance? Okay. Right? So do all of you know what is the least upper bound property or the so-called order completeness axiom? I will state it. Okay. That is going to be, I am going to say, that is the one which makes real analysis tick. Are you able to hear me? Okay? Yeah, sure. So to just quote our modern, Indian experience, that's the Aadhar of real analysis. Okay? For everything you want to do, you need it. Okay? So that's what we want to prove. Give at least some instances. So, in case you find that I am talking too fast or something which I am saying is not understood, please raise your hand. Okay? I would like to. The purpose of this is that you learn something, you also begin to enjoy. That's more important thing. Second part is more important for me. It's not only learning with enjoyment. Okay? So I have a non-empty subset A of R. Is it being projected? Is it something? Yeah, I saw that, right? Okay. Okay. I have a real number alpha in R. I say alpha is an upper bound. I will not write much. I will talk a lot and do not. It's lucky that I'm on your. Don't worry about writing because writing is not all that easy in this room. Okay. And there are books you can read. So I say a real number alpha is an upper bound for the set A if something happens. That is, for every x in A, x must be less than or equal, not strict. Equality is also allowed. You understood that? Then I call it as alpha is an upper bound. So if you give a real number beta, if it's not an upper bound, what does it mean? There is at least one x in A which is strictly greater than alpha. That fact we will be using repeatedly, so understand that. Okay? Very good. Thank you. So among all the upper bounds, see, once alpha is an upper bound, anything greater than alpha is also an upper bound. Okay? Therefore, the best thing I should ask for is, you want to be economical, you want to be optimal. You will ask for the least. If I give a donation, I can get into a college, then I will look for the least donation which will get into my college. Right? Admission. Right? The same way, if I have an upper bound, what I will look for is the least upper bound. Okay? So what is the meaning of least upper bound? I say a real number alpha is the least, I should say a least, but its uniqueness, etc. is assumed, is the least upper bound of A if two things must happen. Okay? What should happen? First, alpha must be an upper bound. Again, remember, it's something like shortest boy. So if I say X is the shortest boy, first he must be a boy. Next, he must be shortest among boys. Right? There may be a girl who is shorter than him. You understand that? So, when I say alpha is the least upper bound of A, first it must be an upper bound. Next, among upper bound, it must be the least. So, if you say beta is an upper bound for A, then I should be able to compare alpha and beta. That I can do, order relation. What do I want? Alpha must be less than or equal to beta. Is that definition clear? All of you must have seen it, right? Okay. Usually, among many teachers will write supremum. I prefer least upper bound because English is already a second language for me. Yeah, least upper bound at least makes sense, like shortest boy. Whereas if you say supremum, okay, I'll keep mum. But I will use supremum once in a while, okay, but that's the word. So I'm not writing, is that clear? Yes? Okay. Suppose alpha is the least upper bound of A, or which is a popular thing is supremum of A. Now suppose I give a beta less than alpha, what can I conclude? It cannot be an upper bound of A, right? So beta is not an upper bound of A. But if something is not an upper bound of A, what does that mean? There is an x in A, so that x must be greater than beta. Very good. So it's always good in analysis to draw number line, because when we introduce real number system, it's purely axiomatic. There exists something like with some property, that's it. Okay, you are not shown it. You understand that? Rational numbers, I know how to write. P upon Q or M upon N, whatever you want, I can do that. But real numbers, it's almost like, don't get offended, it's like saying God exists. Okay? There exists a system with these properties. Okay? Okay, mathematicians likely prove it, there exists. Okay? So, the better thing is to look in terms of number line. As in higher secondary 12th standard, all of us have been told real number system, there is a one-to-one correspondence between points on the number line. Okay, that's always a good thing. People may look down upon, people think that it's not rigorous, it's okay. You understand, make everything rigorous. Okay. So when I say alpha is an upper bound, that means every element x in A must be to the left, right? And alpha is the least upper bound, that means if you give me beta and upper bound of A, then beta should be right. Next, when I say beta is less than alpha, where alpha is the least upper bound, what does that mean? There is an x in A, x is greater than beta. Can it be this side? No, because x will be strictly greater than beta, but alpha is an upper bound. Therefore, it should be x must lie here. You understand? Keep those things in mind. It will help us. So this is the least upper bound definition. So what is the least upper bound property says? The least upper bound property says if somebody can be bought, there is always the minimal price with which it can be bought. Right? If I can get admission with money, I can try to get admission with the lowest denominator. Right? So what does it say? If you can find an upper bound, suppose you give a non-empty subset A, and suppose there is a real number alpha, suppose alpha is an upper bound for A, then what does it say is, then I can certainly find a beta, so that beta is the least upper bound. If you can find somebody who is an upper bound, then I can always find the least upper bound. Does it make sense? Okay. Mathematics is also common sense. Think, okay, that's why I keep giving real life examples, right? If at all you can find this set is bounded above by alpha, then I want to say there exists a beta, so that beta is also an upper bound and it is a least. Very interestingly, the set of rational numbers does not have this property. Right? So what is the LEB property? It says, again the same notation, if there is an alpha in R, so that alpha is equal to an upper bound of A, then there is a beta in R, so that beta is the LEB of A. Okay. This is the property. So what does it mean to say the LEB property fails for Q? That means there is a set of rational numbers A, non-empty subset A of rational numbers, so that there is an alpha where? In Q. There is a rational number alpha, so that alpha is an upper bound of A. But I cannot find a rational number beta, so that beta will be the least upper bound of A. You understand that? Okay. That is the one which distinguishes Q and R. R has something, it looks very similar to Q, okay, with respect to algebraic properties and order relation. But where does it change? Q does not have LEB property, whereas R has the LEB property. Is that understood? Right. So that what we want to claim is it is the Aadhar of real analysis. That is, anything, any major theorem in real analysis uses LEB either directly or indirectly. Sometimes it will layer after layer. That is, you would have proved a lemma, you would have proved a theorem, you would have proved a proposition, you would have proved a lemma, and the last theorem will use all these things. So you may not know the last theorem used LEB, but if you notice, these things might have used. Okay. So it's very strange that a lot of analysts across the world are not aware of this point. Meaning they know LEB property, but they know, if you ask them what is the single most important property for real analysis, real number system, they will usually say because of metric space completeness. That is, every Cauchy sequence is complete. Okay, there are ordered fields in which every Cauchy sequence is complete, but something which you would like to have will not be true. Anyway, I'll come to that. So do you understand what is the LEB property? Yeah. So the aim of this lecture is at least to prove some 3 or 4 results directly from LEB property. Okay. So that to show how to use it. Am I making myself clear? If there is any question or you want any kind of explanation, please raise your hand. I will attend to you. Okay. Right. So we are going to repeatedly use. The moment you give me alpha is the LEB of A, the uniqueness I am not going to touch upon, it's very easy. If alpha is the LEB of A, how do I exploit? That's a fact given to you. Now how do I exploit? In all the proofs, the way you exploit is, look for a beta which is less than alpha, then there will exist an x in A such that x is greater than beta. Then you have to play around with that. Okay? We will see how to do that in a minute. Keep that in mind. The first thing we want to prove is the following property, what is called Archimedean property. It's R. What does Archimedean property say? You start with the natural numbers, right? Then you want to say it's not bounded above in R. What does that mean? No real number alpha is going to be an upper bound for natural numbers. What does that mean? If you give me an alpha, a real number, then it's not an upper bound for n. That means there is a natural number n which is strictly greater than alpha. That's what it claims. If you think of number line, it looks obvious. Right? 1, 2, 3, keep on writing. You give me any alpha, I can go beyond that intuitively. Right? It needs to be proved. It looks obvious, but it needs to be proved. Now you should wonder, one directly gives a proof, but you should wonder why I have to prove it. It looks obvious. Yeah? Why should I prove it? The reason why I should prove that is, I do not know the set of real numbers explicitly. I have no idea. I know it. Something with some property exists. I will give an easy example so that you can appreciate. Suppose I say he is the tallest boy or tallest person in this classroom. It's very easy because I know everybody. I can measure the height and say he is the tallest. Right? Now suppose I want to claim he is the tallest person in the entire campus here. I don't know all the students of the campus. Yeah? But how do I know? But suppose, let's say, okay, before entering the class, there is an electronic machine which measures the length. And the principal tells me, okay, the tallest person in this is something like 6 feet 2 inches, let's say. He has told me. And if I measure his height as 6 feet 2 inches, without knowing everybody, I know extra information. Namely, the tallest person at present in this campus is 6 feet 2 inches. I know this fellow is 6 feet 2 inches. Then I know he is the tallest person. Without knowing everybody, which is just because I had extra information. Do you understand that? Yeah? Now the extra information is this. I do not know R, but you told me R has all the order relations, algebraic properties, but then it has the LEB property. Using that, I want to conclude the set of natural numbers is not bounded above in R. Do all of you understand this? Does it make sense? Right? That's the first simplest instance where you use the LEB property. Right? Namely, the so-called Archimedean property. The set of natural numbers is not bounded above in R. So how do I prove that? Whenever you do, somebody may say that, I claim, but you may claim, no, it's bounded above. I will have an alpha, but I won't tell you. Then what will I do? Then you have to argue by contradiction. So that's the most powerful mathematics, okay, trick we have. So suppose alpha is an upper bound, right? You want to say natural numbers is not bounded above. Assume the contrary. There is a real number alpha, which is an upper bound for n, right? So what does that mean? For every k natural number, k must be less than or equal to alpha, right? Now what did I say? The only way I know how to exploit if I am given a least upper bound is to look for somebody who is less than him. Right? You gave me an alpha, a real number. Now I am dealing with integers, so I want somebody who is less than alpha. What number I will take? I can take alpha minus half, alpha minus 1 upon 20,000, but easiest thing will be take alpha minus 1. Alpha minus 1 is less than alpha. Therefore, since alpha is the least upper bound of n, alpha minus 1 is not an upper bound for n. What does that mean? There is a natural number n which is strictly greater than alpha minus 1. Now it is staring. Write it in your mind. N is strictly greater than alpha minus 1. Then it means n plus 1 is strictly greater than alpha. N is a natural number. Therefore, n plus 1 is a natural number. But that is greater than alpha. Is that a contradiction?
Yes, sir.
Yes, because alpha is supposed to be an upper bound. I don't even need the least upper bound here. You understand that? Therefore, this contradiction shows alpha is not an upper bound. Yeah? Can you just go through the proof for 20 seconds in your mind without writing? Without writing. Is it okay? Right? Look at alpha minus 1. There is a natural number n greater than alpha minus 1. Add 1 to both sides. N plus 1 must be greater than alpha. Remember, I am using all the usual order relation properties, etc., which are also available in Q. But the only thing is, LEB was not available. At least I don't know that. We have to prove it, but we will see. Now let's come back what I said. Why the common misconception that the Cauchy completeness is the most important property for R is wrong, because there exist fields in which you can do order, okay, in which every Cauchy sequence is complete, but the Archimedean property fails. That is, there is a number alpha in that field, so that alpha is an upper bound for a set of natural numbers. Real analysis depends on estimate. So, and estimates usually depend upon the Archimedean property. So, that fails. Okay. And all of these people also heard the word Archimedean fields, non-Archimedean analysis, etc. But they will not appreciate the most important property is the LEB property, not Cauchy completeness. Okay. We are going to prove R is going to be Cauchy complete. Okay. What is the statement? You have a Cauchy sequence xn in R. Then I want to say there is a real number x, so that xn should converge to x. Yeah? Do all of you recall what is the definition of Cauchy sequence? Yes? So I have a sequence xn in R. When do I say xn is Cauchy? You give me an epsilon, there is an n naught, so that whenever m and n are greater than or equal to n naught, modulus xn minus xm should be less than epsilon. All of you know that. So what is that I want to claim? If you give me a Cauchy sequence of real numbers, it converges. That means I have to find a limit. So I have to assert there exists a real number x. That's the first thing. I have to say there is a real number x such that xn converges to x. Yeah? And what is the definition of xn converges to x? For every epsilon positive, there is an n naught, so that modulus xn minus x should be less than epsilon whenever n is greater than or equal to x. So I don't want to write all these things. I'm sure all of you know that, right? Okay? Good. So what is that we want to prove? We want to prove every Cauchy sequence in R is convergent. Am I going fast? Since you already have been exposed to, you have nodding acquaintance with all these concepts, I can go ahead. Otherwise, in a typical classroom, it will take time for me to explain all those things. Are you happy? It's okay?
Yes.
Sure. So I have to prove xn converges to x. All of you must have seen a proof, right? Unless someone just passed the exam now, in which you proved it, it's a, I'll be surprised if you remove the proof of this fact. The coefficient sequence of real numbers is convergent, because the proof is typically what I said earlier. It will say, it will depend upon various previous results. Right? Now I am going to give a proof which will not depend upon anything. You know the definition of convergent sequence, you know the definition of coefficient sequence. I will not talk about every coefficient sequence is bounded. I will not talk about subsequence. I will not talk about monotone subsequence. I will not talk about something like if I have a coefficient sequence, if it has a convergent subsequence, the coefficient sequence converges to that. None of these facts I will need. You understand that? What all I know is definition of convergent sequence, definition of coefficient sequence. I know something about LEB property. That's it. We are going to give a proof. Right? Okay. Sandhana, எப்போ ஆரம்பிச்சேன்? 10:30. Half an hour later. So I am a great believer in working backwards. What is working backwards? Okay, that's a standard trick. When you read hereafter, you learn that. If there is a theorem, that means it's a theorem. Somebody has proved it. So it must be true. Right? If it is true, what should happen? Okay? I work backwards. Anyway, somebody has assured that it's true, then we work. Okay? But if I don't know whether it's true or not, then I have to find a way. But somebody has told it's a true, it's a theorem. For the last 200 years, people have been writing proofs, so it must be true. So let's accept it. Okay, then work backwards. But then I want to use LEB property. That means I want to find an x, that xn converges to x. Okay. So I want to assert the existence of x. What does that mean? I want to use LEB property. That means that x, I should get LEB of a set. That's the first thing that goes to my mind. Right? So that means I have to construct a non-empty subset A of R, so that my x is going to be the LEB of A, and I have to show xn converges to x. Next. Therefore, the A should involve the hypothesis. Hypothesis that x, you are given a coefficient sequence xn. Therefore, A must be constructed out of something to do with xn. Right? And the next thing is working backwards. You told me xn converges to x. Right? That means what? For a given epsilon, give me any epsilon positive. Right? Then I know there is an n, capital N, or n naught. Right? Another standard trick in mathematics is there are too many variables. What you do is you freeze one variable, let the other variable to vary, and try to understand. Okay? If you look at the price of a commodity, the price is a function of various, okay, the input cost, and what is the next today? GST involved, right? And inflation, and if it depends on the import, then foreign exchange, right? These are the functions and variables for the function, namely price of the end product. Then what do? As an economist, you try to freeze one, assume that inflation is not going to be varying, then what is the result? Like that. So this is the only thing. So look at that. In this inequality, there are two variables, m and n are allowed to vary. So I just keep one fixed set. What number I will choose? That is true for all m and n greater than or equal to n naught. So I freeze one n to be n naught. Right? Then what do I have? I will revert to this picture. So that's going to be, I have x n naught, and this is going to be so if m is greater than or equal to n naught, my xm should lie in this interval. Do you understand that? Yes? Right? Mod x minus a less than epsilon. What does it mean? X lies in m minus epsilon to A plus epsilon. That's what I am using. Okay. Now what does it say? It says my x has to be greater than xn naught minus epsilon. Right? You understand that? Okay. So my x I can think of as though it is going to be got out of the LUB. Suppose this is my x. Look at x minus epsilon. This x is a stupid thing to say, but then that is. Look at the open interval minus infinity x. It is the LUB of x. Therefore, start with any y here. Okay, then it is going to be LUB of all these numbers. You understand? So this x is going to be LUB of xn naught minus epsilon. But what is the property of xn naught minus epsilon? It says that there exists infinitely many m such that xm is greater than xn naught minus epsilon. Is that right? That's what I wrote. For all m greater than or equal to n naught, xm has to be greater than xn naught minus epsilon. So this is the one which is going to allow me how to define the set A. Okay, how do I define? I define A to be, I will write, okay, I will write x, but that's not the x which we want in mind. X is a real number, so that there exists infinite number of k, so that xk is greater than x. So, okay, this x is not the moment. Okay, if you want, I will just do it. I will write L. Okay, L is going to be our limit, so I will just. Please understand what is that we are looking for. I am looking for any real number x so that there exists infinitely many k so that xk is greater than x. Right? Is the set non-empty? Yes, it's non-empty because you give me any positive epsilon, then there is an n naught because of the Cauchy condition, and just now I proved for all m greater than or equal to n naught, xm is greater than xn naught minus epsilon. Therefore, there exists infinitely many m. Is that okay? Therefore, this set is not empty. And how many elements I have found? Allegedly many. So, what are they? For every epsilon, you have an n naught. That n naught depends on epsilon, but I am not writing that. Okay? And look at the corresponding number xn naught minus epsilon. That number, that real number is going to be a member of the set A. Is that clear to all? No doubt? Okay. Next, I want to talk about the LUB of A. So, what I have to do? I have to say there exists at least one upper bound. Then only LUB property will say that there is a real number which will be the least upper bound. You know, right? So, I have to prove there is an upper bound. Let's try to understand the Cauchy criterion. What does it say? So, I have xn naught minus epsilon, xn naught plus epsilon. Let's look at m greater than xn naught. Now, suppose I have a k in n so that xk is greater than xn naught plus epsilon. What can you say about that k? If k is greater than or equal to n naught, then it cannot, right? Because xm will lie in that interval, therefore xm will be less than xn naught plus epsilon. Is that clear? Yeah? Therefore, if at all there is a case so that xk is greater than xn naught plus epsilon, that k should lie between 1 and n naught minus 1, but let us not worry about 1 to n naught. Is that okay? Not all of them may have, but if at all xk has to be greater than xn naught plus epsilon, then k must lie between 1 and n naught. Do all of you understand that? Therefore, only finitely many xk can be greater than xn naught plus epsilon. Is that logic clear? Yes? Very good. Okay. Now what I am going to claim? I want to claim the set A has an upper bound, right? So what I claim is you give me an epsilon. I said xn naught minus epsilon is an element of the set A. I am also going to claim xn naught plus epsilon is an upper bound. You understand that? Yeah, it's an upper bound for the set A. Again proved by contradiction. Are you with me? Yes? Okay. So suppose xn naught plus epsilon is not an upper bound. I'll keep this in mind. This is what is needed. This also is needed. Suppose false. What does that mean? That means this is not an upper bound for the set A. What does that mean? There is an x which is strictly greater than xn naught. Okay, you don't need the picture. Okay, because sometimes people will remember the picture, they think the proof is not rigorous. It's not. For me, the picture gives me rigorous proof. Okay, there is an x where in A, yeah, so that x is strictly greater than xn naught plus epsilon. Now, where does x belong to? It belongs to A. If it belongs to A, what does it mean? There exists infinitely many k which is greater than x, but x itself is greater than xn naught plus epsilon. That means there exists infinitely many k such that xk is greater than xn naught plus epsilon. That's a contradiction. Because what did you prove? If xk is greater than xn naught plus epsilon, then the k is only finitely many, 1 to n naught at most. But now you claim there exists infinitely many. Is the proof clear? I'll just give you 10 seconds. Go through the proof in mind. How did I claim xn naught plus epsilon is an upper bound? If not, there is an x which is strictly greater than xn naught plus epsilon. Now x belongs to A. That means there exists infinitely many k so that xk is to the right of x. That means xk is greater than x, that x is greater than xn naught plus epsilon. Right? But can it happen? No, we already proved. If at all xk is greater than xn naught plus epsilon, k lies between 1 and n naught. Therefore, that contradiction shows our assumption is wrong. Therefore, xn naught plus epsilon is an upper bound. Do all of you understand? So, I have proved A is non-empty and A is bounded above. How many upper bounds I have given? As many as you want. You give me an epsilon, then xn naught plus epsilon. That x naught is also not unique. You understand that? Yeah, there will be any. So, this is a non-empty subset bounded above. So, what are the two things we have observed? This n naught depends upon epsilon. You give me an epsilon, then by Cauchy criterion there is one n naught, that xn naught minus epsilon has to be an element of A. 2, for every epsilon, these are the two facts. What did I use? I use only the definition of Cauchy sequence. Is that okay? Nothing more. Right? Now the set A is non-empty and bounded above in R. Therefore, the LEB property, what do I know? There is a real number. Let me call it L for limit. Okay? L in R, so that L will be the least upper bound of A. Right? What do I want to claim? I want to claim that L xn converges to L. Okay? I want to prove that. Yeah? Yes?
So, but this n naught depends on epsilon.
Yeah.
And we are saying.
And that n naught is also not unique.
Yeah.
If n naught happens, any n greater than n naught will also serve the purpose. It doesn't matter.
So when we are saying that for all epsilon, xn naught minus epsilon is in A.
You give an epsilon by Cauchy completeness, you have to assure me there is n naught. She may give me some other n naught. I don't care. Give me one n. I have proved xn naught minus epsilon is an element. That's it. Okay. You just have to prove it's non-empty. And similarly, you have to prove it is bounded above. It has an upper bound. I proved it. Okay. Think about this kind of proof. Okay, it takes time. Okay. Now I want to prove xn converges to L. To prove xn converges to L, what is it I have to do? You are going to give me an epsilon. I have to find some n naught, so that modulus xn minus L must be less than epsilon. Right? Good. If I prove mod xn minus L is less than 2 epsilon, will you agree with me? Otherwise, I have to do start with epsilon by 2. Okay? Right? Okay. So I want to prove, essentially I want to estimate this. See this, the entire analysis, the key word, the mantra you have to keep chanting is whenever you want to prove a theorem in analysis, you have to estimate something or other. Okay, that's going to be the theme of Professor Santhanam's. By the way, it's a Santhanam, not Santhanam. I will write in Devanagari. Is it okay if I write like this? You want Sanskrit? This is the one? For you, no, I know. See, the Hindi Devanagari in the Sanskrit, for dot you have a different way. You would write that. And my name is not Kumarasan. Yeah. The moment you say K-U-M-A-R, then your natural instinct is to pronounce it as Kumar. Then you have to end it with the Esan, then you say Kumarasan. Okay? Okay, it's a Kumarism. Okay. Anyway, forget it. I don't pronounce your name correctly. You don't know to pronounce my name correctly either. That's fine. Okay? Now come back. So, the theme of analysis is someone I have to estimate something. When I want to prove something, xn converges to L, that means I have to estimate. Epsilon, n naught, etc. comes later. I have to estimate. When I want to do estimate, there is only one trick, namely triangle inequality and what we call Curry, which we will talk about, but let's not worry. So I want to estimate. Do I know how to estimate? I don't know. But what I know is, I know how to estimate xn and xm. If you give an epsilon, I know how to estimate xn and xm if n and m are very large. You understand that? So that is the Curry leaf. Is it okay? For any m, it's true. Independent, it's a triangle inequality, right? The Curry leaf trick, what it says is, you choose your m smartly, wisely, carefully, so that you achieve the purpose. What m I want to choose? I want to say the entire thing should be less than epsilon. So I can choose the first term is less than epsilon by 2, second term is epsilon by 2. But that's some kind of an inbuilt symmetry, but I can also make sure the first term is epsilon by 10, second term is less than epsilon 9 epsilon by 10 also. You understand? But symmetry suggests, I reckon. Now, how do I make this less than epsilon by 2, the first term? That's because you told me xn is Cauchy. Therefore, if you give an epsilon by 2, there is an n naught. Or just to keep it epsilon. Okay, finally we want to prove less than 2 epsilon, right? So life will be simpler. Otherwise, notation is ugly. So for epsilon, I know there is an n naught, so that mod xn minus xm will be less than epsilon for any n and m greater than equal to n naught. This n naught depends on epsilon, don't worry. Okay? Right? But then I have to make sure this m xn minus L is also less than epsilon. Now remember, this m can be anything greater than n naught, but as I said, I don't like this kind of, anything will work. It's like saying, I want the job to be done. You just give me some money, it will work. That's not enough. You have to tell me how much money I have to give. Right? The job would have been done for 10 rupees, I may end up paying 1,000 rupees stupidly. Or I may give 5 rupees, he may get irritated, my file will be delayed forever. Right? So I should know how much I have to give properly. So here also the same thing. So instead of saying any m will do, greater than or equal to n naught, let us specify. The easiest thing is, as I did earlier, take x n naught itself. Yeah? So, this I can write now. This is strictly less than epsilon. Is it okay? By our choice. Now let's look at this. What does this say? Mod xn naught minus L should be less than epsilon or less than or equal to epsilon also do. Is it okay? Do I know that? Yes. Why? How do I know that? It says my L should lie in the interval xn naught minus epsilon to xn naught plus epsilon. I am not looking at L minus epsilon to LL plus epsilon. Looking at, you understand? There are two ways, right? When I say mod A minus B is less than epsilon, A is less than, A lies in B minus epsilon to B plus epsilon, or B lies in A minus epsilon to A plus epsilon, because mod is symmetry. Right? Mod x minus y is same as mod y minus x. So here what do I want? I want to say L lies in the interval xn naught minus epsilon. See, think, I am working backwards all the time. So, I want to say L lies here. But that means L must be greater than, okay, L xn naught, at least greater than or equal to will do. So let us make it even greater than or equal to. Right? Do I know that? I know that. Why? For any given epsilon, I proved xn naught minus epsilon is an element of A, and L is the least upper bound of A, in particular an upper bound of A. Therefore, what's the relation between xn naught minus epsilon and L? Xn naught minus epsilon is less than or equal to L. Right? Very good. Now, L is the least upper bound of A. But what did I prove about xn naught plus epsilon? It's an upper bound of A. Therefore, what's the relation between L and that? L is less than or equal to xn naught plus epsilon. That means my L lies in the closed interval xn naught minus epsilon to xn naught plus epsilon. That means modulus of xn naught minus L is less than or equal to epsilon. Therefore, the second term is less than or equal to epsilon, but the first term is less than epsilon. Then what did I prove? For any n greater than or equal to n naught, I proved mod xn minus L is less than 2 epsilon. Okay? So as a teacher, I have a kind of a principle. Many of the teachers try to believe I explained so well, okay, everything threadbare, so my students, my audience should understand 100%. That's a delusion. Okay, I never believe that. Okay, that's why teachers get irritated if you say you don't understand. Oh, I explained so well. Okay, no, because understanding is yours, it's not mine. Okay, my teaching helps you to look at a certain direction so that you see what is there. That seeing is yours. That I can't help. You understand? So I'll be happy if you understood 50 to 60% of what I talked about. Right? The later you have to go and read and think about, okay, reflect upon, then you will understand. Okay? So when you become teacher also, don't delude yourself. I am a greatest teacher, so whatever I explain, my audience should understand. No. Understanding is his business, not yours. So you can't interfere. Okay. Think about, so what did we prove? We proved any Cauchy sequence converges to L. All these proofs, I think, yeah, he had given an article, the role of LUV, you will see the proof there. Okay? So you can read it. Now just reflect upon the proof. What are the things I used? Did I use Cauchy sequence is bounded? Did I talk about any convergence subsequence? Did I talk about monotone?
No, sir.
What did I need? I needed the notion of only the definition of Cauchy sequence, the definition of convergence sequence, and upper bound LEB. That's it. Okay. This is the simplest proof on earth for Cauchy combinations of R. It's a challenge. Okay. You just go back look at your favorite notebook or class notes, try to see how the theorem was proved. You would have used whatever I said earlier. So you would not understood the LEB was the clinching evidence. Okay, as they would call it DNA footprint to nail the ancestor of the theorem. The theorem, okay, the Cauchy-Combinatorics theorem depended only on the LEB property. Is it okay? Since I have a few other things, I don't want to spend upon too much time, but just to give an idea, please go through that article if you are really thrilled, excited. So I started at 10:30, right? Okay. So 27 more. Okay, I will prove another big theorem. Yeah.
So you have 11:45. 11:45. Half an hour is still left. Half an hour is still left.
Yeah, right. That's cutting down 7 minutes for me. Okay. Okay, then I will start with the next theorem. There are some smaller results also one can do. You can check nested interval theorem. Again, you may not remember the proof. Usually they will write AN, BN, then they will say AN is increasing, BN is decreasing, monotone convergence, okay, monotone sequence, their convergence, etc. you will use, right? You will see, don't need that. You need only LEB. That's very obvious, but let's not. But let's do a slightly difficult theorem, which takes a lot of time. And
Please raise the mic a bit above.
pardon me?
Sir, this smaller mic, please raise it a bit above.
It was high enough, but still. Can you fix it? Yeah. The only thing is we should not. Are you okay? Somehow I'm not okay. Where does it sit? So next theorem we want to prove is the so-called intermediate duality theorem. Yeah? That depends upon continuity. Can I just assume continuity? I will just recall if you want, because I will recall anyway, because I want to make an observation. Okay? First, before that, I would like you to, all of you, I now asked you not to write, right? Now you don't write, draw a picture. Right? Take an interval AB, closed interval. I want to draw just a continuous function, so that f at A must be less than 0, f at B must be positive, right? And remember your 12th standard teacher, whenever you draw the graph of a continuous function, you should not lift your hand off the paper. Draw it. You understand? Just some graph. You don't have to worry about. Make sure it's a graph of a function. That means it should not. No vertical line should cut the graph at 12 places. When in a hurry, you may make that mistake. You can't do like this. You understand? If I do like that, it cuts at 3 points. Draw. I want f to assume negative value at A, assume positive value at B. Yeah? On the interval. Draw. Anything, don't worry. See, this is what you are missing. Math is fun. You should enjoy. Very small picture. Compare your picture with others. See, that guy takes a lot of time. How about you? See, look at that. I am not giving any function. You understand that? But you know what your function is. You know how to draw a graph. And okay. And you also have the golden rule given by your junior college teacher. Okay. Try it. The only condition is f at A must be negative. Right? And I am sure you would chalked A and B and the positive x-axis. Therefore, it should be traveling from the fourth quadrant to the first quadrant. I have given you enough. So, check. Compare your picture with your friends. So, do all of you understand something? What happens? It has to cut the x-axis. What does that mean? It is same as saying there is a C in the interval AB, such that f of C must be 0. That's a value intermediate between positive and negative. That's what we want to prove. Yeah? So that's a theorem. It's a special case, but the general case is utter triviality from that. Corollary. It's again for convenience, you can also assume f of A is positive, f of B is negative. It's the same thing. Then I want to say there is a C. I mean, teacher will say, no, you should write open interval, but then no, f of A cannot be C, and B cannot be C. Therefore, it has to be in the open interval. It's obvious deduction. Right? Okay. Now, how do I prove that? Again, look at all your pictures. Right? Can you think of C as the LUB of a suitably defined subset? Look at your picture. Does it suggest a subset A so that the point, and all of you are been very simplistic. Now, I don't think many of you have drawn this kind of picture. Most of you have drawn only this picture, right? Yes? It could keep meeting many places, right? Yeah, anybody's career has lots of up and down, not only one up and down. Right? Now, so this is the point. Let's look at your simplest picture, but this also is okay. This is the first point I want to capture. Because in your case there is only one C, so you are happy. But in my case there are C1, C2, C3, C4 and C5. So I want to concentrate the first point, C1, from the left side. Okay? Starting from A. How will I capture that C in your picture? I want it to be LUB. I will look at the interval closed at A, open at C. But that's not enough. What you have to say is something to do with function, right? I want to prove something with the function. Therefore, the set should depend, the definition should depend upon the function. It's not only the open interval AC, because that means you already know C. So how do I do that? Look at any x, okay, which is less than C. On the interval A to x, what do I see? It always remains negative. Right? Not only at x, on the entire interval A to x, my f of t is always negative. Therefore, how do I formulate the set A? Can somebody suggest? Right? So, intuitively this set is what you have written. That captures all the things closed at A, open at your C. Whatever the first C which comes from A. As you progress from A to B, the first C. In my case there will be many, in your case there is only one. Is that okay?
Take less than equal to 0.
You can take that also, but then I don't know whether it's going to be 0. It is not going to matter. Is that okay? Yeah? Right. Now there is something very interesting before going further. I want to prove A is non-empty. For certainly A is bounded above. Because if A is non-empty, it is bounded above. Because any real x in A must be less than or equal to B. The crucial thing is it is non-empty. Then let C be the least upper bound of that set A. Then I will say f of C must be 0. Is that okay? Right. The way I prove f of C is 0 is using law of trichotomy. F of C is a real number. Right? Either it has to be 0, in which case I am happy. Right? Mogambo Kushwa. Right? Okay. If it's not, law of trichotomy says f of c must be positive or f of c must be negative. Then I will say in each of the cases I will have a contradiction. Right? Therefore, by law of trichotomy I will be compelled to conclude f of c must be 0. Is it all right? That's what we want. The clue lies in a small observation. What is a small observation? Suppose f is a continuous function, right? And suppose f of c is positive. Then in an interval around c, f will remain positive. Right? Look at your picture. In c minus delta and c plus delta, you can find a delta so that it has remain positive. Similarly, if f of c is negative, f of c, then there is a delta so that on the interval it will remain negative. So that is a local behavior, continuity. I don't even know whether it's continuous to all other points. I only know f is continuous at c. That is good enough to tell me that f will retain the same sign in an interval around c. Right? We will prove it by using definition. Okay? Because then the proof will be utterly trivial. Do you understand what I have written? I only know f is continuous at c. I am assuming f of c is positive. Then I want to say there is an interval around c. That is, there is a delta. So that look at c minus delta to c plus delta. For all x in that, I want fx must be positive. But all points may not be in the domain, so intersect with the domain. Right? For example, suppose my c is an endpoint, right, a to b, and f of a is positive. Then what does it mean? For all x in the interval closed at a, open at a plus delta. Because a minus delta at a plus delta intersect with the closed interval a, b, then I will get only on that. Do you understand that? And similarly, if f of c is negative, similar result. Okay? So this is very easy to prove using continuity. Again, it will not, if you use modulus, you will get trouble. So what you do is, f is continuous at c, right? Now let's look at again picture. Remember, I always start with the picture to make me understand what is happening. Then the proof will be written, pure notation analysis. Okay? So I have 0, you gave me f of c. Right? What do I want? I want something so that f of x should be positive, right? Now let's look at epsilon equal to f of c by 2. Then this is f of c by 2. This is 3 f of c by 2. Right? F of c plus minus epsilon to f of c plus epsilon, right? Then in that interval, every point is positive. But what do I know? For this epsilon, since f is continuous at delta, I know continuous at c, there is a delta positive, so that for all x in c minus delta to c plus delta, intersect with the domain f, my f of x should lie in this interval. Right? If f of x lies in the interval, f of x must be greater than the left end point, that is f of c by 2. Therefore, what do I conclude? For all x in the specified range, f of x must be positive. Do all of you understand? Just take 10 minutes, make sure, because this is the simplest observation. This is what you had already seen. Suppose xn is the sequence which converges to x. If x is positive, after a while all my xn should be positive. It's the same thing. Suppose I start with x in the domain, and x is also here, then I know fx must lie in this interval. That means fx must be greater than this. Therefore, it must be positive. Is that okay? Similarly for negatives. Did I use f is continuous on the entire domain? No. I use only f is continuous at the specified point, nothing more. Do all of you understand that? Yes. Yeah? Now let's go to prove our result. What is our x? This is x in AB. So that for all t in A to x, f of t is less than 0. You can make less than equal to, but doesn't matter. Yeah? Now this set is non-empty. What does that mean? I have to find an x so that x belongs to this. That means I have to find an for every t, right? Usually, I don't know your definition of interval. If you look at my book also, for me definition of interval is give me any two real numbers a and b, any two real numbers. I can define interval, open interval AB, semi-closed interval, closed interval, or infinite interval also. Because if A is greater than B, then you have to look for an x which is greater than B and less than A. That's empty, right? So it makes sense. Do you understand that? But anyway, it's a kind of contentious issue. Okay. Therefore, if according to me, I can take x equal to A, because that's a genuine interval for me. You understand that? For any two real numbers A and B, I can define is what I said. If you accept my definition, I already found it. Now you say, no, that's not the way I learned. A must be less than B. Then I am in trouble. Do you understand that? Yes? What do I do? Now I will look at. You said f of A is negative. Therefore, by the last lemma, there is a delta so that A minus delta to A plus delta intersected with the interval AB. Right? What should happen? F of t will be negative. Right? That is closed at A, open at A plus delta. But therefore, I can take closed at A plus delta by 2. For every t on that, f of t must be negative. Therefore, I have proved A plus delta by 2 must be an element of A, capital A. Is that all right? That argument is also needed later, so let me write it. This is by the last lemma, right? Therefore, if I take A2, A plus delta by 2 for every t in the closed interval, this happens. Do you accept it? Yes? Therefore, A plus delta by 2 belong to A. Therefore, A is non-empty. Yeah? And its bounded above we already observed. Every x there must be less than or equal to B. Therefore, what do I know? By the LEB property, there is a C, a real number, so that C equal to the LEB, least upper bound of A. What do I want to claim? I want to claim f of C is 0. Now the proof is essentially cakewalk. Okay? Is that clear? Let C be the least upper bound of A. I want to prove f of C is, I will use law of trichotomy. Suppose f of C is positive. Then I have to arrive at a contradiction, right? Now the first thing is, the LEB property provided a real number C, but then I have to make sure that C lies in the interval AB, because I want to talk about continuity of F at C. So I have to make sure that C lies in the interval. Why does it lie in the interval? C is an upper bound for the set A, and A plus delta by 2 belong to A. Therefore, C must be greater than or equal to A plus delta by 2 and hence greater than or equal to A. Is that clear? And C is the least upper bound for the set A, but B is an upper bound for the set A. Therefore, C must be less than or equal to B. Therefore, A is less than or equal to C, less than or equal to B. Therefore, C is a genuine element of the interval A. Therefore, I can talk about continuity of F at C, right? Then only I can talk about f of C has to be 0 or anything, right? I just forgot it, I just proved it. Therefore, C is a genuine element of the interval. Then I claim f of C must be 0, right? Suppose f of C is positive. Okay, what's the contradiction I will get? So, let us look at, I will draw a magnified picture. See, right? Now the C, remember, I claim f of C is positive. The C could have been B. Right? You understand that? C could have been B. Right. Now let's look at, how do I argue now? Now since f of C is positive, what do I know? There is an interval delta positive, so that on C minus delta to C plus delta, my f of t remains positive. Is that okay? So there is a possibility C could be B, but that doesn't matter now. You will see that. So the picture is going to be, there is a C minus delta. To C, for every t, f of t must be positive. Do you accept it? Yeah? Now do you see a problem? Okay, this C could have well be very well with B, but I am not looking at the other delta part. You understand that? Yes? So, for every t here, C minus delta to C, okay, this f of t must be positive by the observation which I already made. Now what is the problem? Now remember, C minus delta, again I can choose a delta so that C minus delta is greater than A. Because one delta works, I can, for every delta smaller than also it will work, right? And C minus delta to C plus delta it is positive, then C minus delta 1 to C plus delta 1 will also it will remain positive. Delta 1 is less than delta. Therefore I can choose a delta such that C minus delta is also greater than A. Right? Therefore C minus delta is less than C, but C is the least upper bound. We have to exploit the fact C is the least upper bound. Now you gave me C minus delta which is less than C. Therefore what can I conclude? C minus delta is not an upper bound for the set A. What does that mean? That means there is an X in A so that which is strictly greater than C minus delta. Where does X belong to? X belong to A. Right? Since X belongs to A, what do I know? On the interval A to X, f of t is less than 0. But then my choice on C minus delta to C plus delta, it is positive. Therefore, if I take the midpoint of C minus delta to X, at that point it has to be positive as well as negative. That contradicts law of trichotomy. You understand? So what is it? What is my conclusion? F of C positive is ruled out. Yeah? Next, what is that I have to claim? F of C negative. That proof is again easy. I can keep the same picture except this X I will change. F of C is negative. Remember, I already proved C is lies in the boundary A to B, but you say f of C is negative, therefore C cannot be B. F of B is positive, right? Therefore f of C must be, C must be less than, that's very crucial, right? Since C is strictly less than B, by the last lemma f is continuous at C, therefore there is a delta positive, such that on the interval C minus delta to C plus delta, f of C will remain negative, right? But since C is less than B, I can choose delta small enough so that C minus delta to C plus delta, that is C plus delta is less than B. On this interval, what do I know? F is negative. But again, there is a contradiction. Why? Now let's look at C plus delta by 2, the closed interval A to B, right? You understand? On this interval, it is negative. Make sure, okay? Don't lose thread. 90 minutes, say 80 minutes a long duration, so your attention span may go down. Okay, let's go back. Yeah. So what did I know? There is a C, so that on C minus delta to C plus delta, it has to remain negative. Yeah? Right. Now how do I conclude? On the interval A to C plus delta by 2, the closed interval, it is negative. Again I have to use C is LUB. Right? So what do I know? Now C minus delta is less than C. Therefore there exists an X in A such that it lies here. Where does X lie? X lies in the interval C minus delta to C. C minus delta open, C closed. Yes or no? This is less than the least upper bound, therefore this is not an upper bound, therefore there is an X. Right? In A, so that X is greater than C minus delta. You understand that? Now since X belongs to A, on this interval I know it is negative, and on this interval I know it is negative. Therefore on the union, that is A to C plus delta by 2, the function is negative. So what does it allow me to conclude about C plus delta by 2? C plus delta by 2 must be an element of, must be in A. Yeah, right, must be an element of A. Right? But that's a contradiction. Why? C is an upper bound of A, but C plus delta by 2 is strictly greater than C. This contradiction shows f of C cannot be negative either. So I already proved it cannot be positive, it cannot be negative. Law of trichotomy forces me to conclude f of C is less than 0. Is the proof okay? That's it. Any questions? And all these proofs can be found in the article which is given to you. And there is also a book written by me. It's a sales talk now. Okay. I say there is always a commercial break, right? Okay, written by me. I think what is it? The basic course in real analysis, written by my Mr. Ajit Kumar, Dr. Ajit Kumar, and myself. The only problem is it may be, if you look for Amazon and Flipkart, you may find only the US version, asking you to spend your father's entire savings. Okay, there is an Indian edition. Search for it.